Green Rush, Mining the Energy Revolution with Matt Watson.
Welcome to Green Rush, Mining the Energy Revolution. I'm your host, Matt Watson. Each week we take on this periodical table and we pick an additional metal that we can talk about, and we'll even talk about some of the technologies involved in this clean energy transition. That's today's topic, the hydrogen economy and platinum group metals. Our special guest this week from Heraeus, Mr. Phillip Walter. He's the Executive Vice President of Business Line Systems for Heraeus. Phillip, welcome to the program.
Thank you, Matt. Thank you for having me.
Oh, not a problem. And just to set the plate for our listeners, Phillip and I have a relationship that goes back a number of years. Heraeus is a phenomenal precious metals processor. We want to give, I think, some of these major processors a chance to kick in their nickel's worth on some of these transitions. So why don't we talk about that first? Heraeus on this slide here gives some of the kind of the key pictures of Heraeus. Now, Heraeus, I've done a lot of business with over the years. I'm sure I've purchased over $100 million in platinum group metals with Heraeus in my time. There's a large, what I call their mothership, their headquarters in Hanau, Germany. Basically, they dominate an entire city, just about an hour outside of Frankfurt. That's where Phillip resides, and Phillip, you've worn a number of hats with Heraeus over the past couple of years. Everything from leading R&D, and now you're focusing on the hydrogen business unit. It sounds like, is that right?
That's correct. I basically joined Heraeus in R&D roughly 7 years ago, and then moved into business development and new business development. And of course, hydrogen is an important topic for platinum group metals. So it ended up in an own business line, which I have the pleasure to lead now since January 1st, 2024.
And so just to give people some context, I always talk about the total available market with precious metals. If you take all the troy ounces produced, both through mining and refine, and just scale it against the dollars per troy ounce, in total, precious metals is about a $350 billion total available market each year. And here's Heraeus with about $30 billion in sales each year. They're roughly 10% of the market share of all precious metals, gold, silver, and all the platinum group metals. Just to give our audience some context, you're certainly one of what I would call the big five precious metals processors, with competitors including Johnson Matthey, BASF, Umicore, and Tanaka being the other four of the big five. So it's great to have Phillip here. I also want to emphasize Heraeus, just a little bit of a sales plug. They have refining and collection networks throughout the planet here, including mainland China. So I think they're really well established with a number of recycling centers and trading desks throughout each of the major time zones. So again, very much an international outfit. So the reason I asked Phillip to join us today, he's been traveling so much. He's joining every hydrogen conference you can imagine. He's a well-traveled individual. So he's become the face of precious metals and PGMs for this hydrogen economy in a lot of respects. I hope you don't mind that characterization, Phillip.
It's maybe a little bit exaggerated.
So I wanted to get into here with some of the Heraeus material that you've used in the past, Phillip, just to give people a sense of how platinum group metals, what products do these products do you touch with the PGMs? Why don't you walk us through a little bit?
Matt, you know me, right? I usually say actually platinum group metals or precious metals in general, in particular platinum group metals and hydrogen, they belong together, right? If you look at it from a chemical perspective, these guys have a unique position in electrochemistry, and that's why they simply belong together. And if you look at the various applications, they cover the full value chain, starting basically from the electrocatalysts for the production of hydrogen here. Proton Exchange Membrane electrolysis is well known. Having said that, one could also imagine other electrolyzer technologies where platinum group metals can play a role. They might not have to, but in order to get a performance, especially in the gigawatt scale, they might in the future.
Right.
So then we're talking about electrocatalysts for electrolysis. We can talk about, as an application, the coating of bipolar plates or porous transport layers to get some stability or some protection against corrosion, as well as the conductivity is a major topic. And then everything around purifying hydrogen or removing oxygen from a hydrogen stream, or vice versa, removing oxygen from a hydrogen stream. Here,
Right.
platinum group metals-based catalysts can play a role. Also, palladium membranes are in discussion. And there are a variety of catalytic uses you can think of, for example, for the synthesis of ammonia in low-pressure processes. So that means not Haber-Bosch, right? Because there it's an iron catalyst mainly. But of course, if you reduce the temperature, precious metals come handy, especially the ruthenium in this respect. And then for making transferring CO2 into methane or methanol, there are technologies available to make that by using platinum group metals. This said, it's probably not so common and might not be so cost competitive with other solutions. But nevertheless, it's possible. And then there is the area of liquid organic hydrogen carriers, the basically organic molecules, which can be charged with hydrogen, and the hydrogen can be released again. And here we are talking about also again platinum group metal-based catalysts. And last but not least, the big application also in the future are fuel cells. Here, platinum on carbon type catalysts are used for basically synthesizing water out of hydrogen and oxygen, and by doing so, you release energy.
I hope you don't mind. I annotated your chart a little bit with, people get a little bit confused. I get questions, I know, in the past about PEM electrolyzers versus PEM fuel cells. That's confusing to some folks. PEM electrolyzers are used for producing the hydrogen, and presumably a green hydrogen. And they put this in the category of power to gas. Right, electrolyzers are very much an energy-intensive application to be able to generate this hydrogen. So you generate the hydrogen with the PEM electrolyzer, and then you can consume that hydrogen and take it the other way, take this hydrogen gas, convert it into power, mostly to drive transportation applications. And so when we talk about fuel cell vehicles like the Toyota Mirai, that's an application of a PEM fuel cell where you have tanks of hydrogen on board that you then power your vehicle. So just to give people that perspective of production of hydrogen versus consumption. And so PEMs are on both sides of that. On the electrolyzer side, these are much more iridium-centric platinum group metals that are involved in the loadings here. When you're on the transportation side, it's very much a platinum-driven application. So as we try to scale vehicles, platinum becomes the key. Is that right?
You're right. In general, I think if I might rephrase it a little bit. So platinum and iridium are essential for the PEM electrolysis.
Right.
Platinum is essential for the fuel cells. However, you also find iridium used in fuel cells as a cell reversal additive. But this is not a must, right? So this is you can actually deal with cell reversal also from a system side. And that's why very often this is not put into the game. But iridium dioxide, for example, is used also there. The market tells us basically this is declining. Having said that, with an increasing number of fuel cells, let's see when it's going to really decline. But this is another application of iridium in the hydrogen economy, in the hydrogen sector.
Fantastic. Okay. And so we're gonna there's a few slides here and some content on iridium that we've got to get through. I know iridium is a challenge. I know Johnson Matthey and Furia Metals and others are all speaking about the need to design thrift iridium. So why don't we get into that here quickly? What sort of thrifting do we need to see, Philip?
I think it is always, there are two elements basically. On the one hand, it's of course how much iridium is needed, and then the other question is how much iridium is available. Right. And we are talking here first of all about primary material, not secondary material from recycling, because usually secondary material is already belonging to someone. Someone is owning it and is probably reused in an existing application. There are a few exceptions eventually, but just to take this as an assumption. And if you're talking about the capacity, I think there are wild numbers around in terms of electrolyzer capacity. If we use a more realistic approach, and we are assuming 25-30% share of this electrolyzer capacities, because there's not only PEM technology as a solution. Then we are ending up with roughly around 70 gigawatt, and this is a figure from 2022, 2023. So it might have changed a little bit, but I don't think it has. It's still a fair estimate.
I think so too. Yes.
And if you basically move into the loading, and that is a critical question, and that's why we're talking about thrifting. I think compared to maybe a couple of years ago, when you used around 1 metric ton of iridium per gigawatt, this has come down now to roughly 400 kilograms per gigawatt. Having said that, with this assumption as an average, you come up with a figure of around a need of 28 tons. However, what's available for new applications is roughly around 12 tons, so maybe 1 to 2 metric tons per year. And of course, this is a cumulative assumption from now until 2030, calculation from now until 2030. So 12 tons cumulatively are available, and 28 tons would be needed for all these gigawatt capacities until 2030. And with thrifting, you basically, and that is now what we talk about catalyst technology, you can reduce the loading from 0.4 grams per kilowatt or 400 kilograms per gigawatt down to 0.1 gram per kilowatt, or in other words, 100 kilograms per gigawatt, or even lower, depending on the optimized stack, basically.
Right. And just to come at it,
thrifting. Sorry, go ahead.
I was going to say, just to come at it at a slightly different angle, just to give people the mind number. So roughly 8.5 to 10 tons a year are come out of the ground. And I think a fairly equivalent number through secondary refine as well. So, this is really a constraint, a minor PGM, right? A subset of the platinum group metals.
Yes.
Very small and yet so crucial. That's why you hear so much discussion about iridium. How are we going to design thrift this to get this to be scalable? So fantastic. I like the way you frame that. And I know this is technical for many folks, but unfortunately, this is a technical topic, so there's no avoiding it. So please continue, Philip.
You made a very good point on the availability, and of course, iridium is not mined as iridium; it's mined in a basket. Means you have it's a byproduct of platinum mining, and that's basically also determining how much iridium is available. It's how without platinum mining, no iridium, and that is of course something which has to be looked at when talking about the availability of iridium.
Agreed. Very well put. So, people, we hear a lot of talk about iridium black, iridium oxides. Why don't you get a little bit more into this oxide discussion and kind of set the tone for the design trajectory? Where are folks going to take this from a configuration perspective to get the maximum performance?
Mm-hmm. Yeah, so I think iridium black is a catalyst in the PEM electrolysis since many years, but of course it results in the higher loadings. So now, and by applying standard catalyst principles, so to say, you of course try first to dilute the iridium with other elements. In this respect, you're making iridium dioxide, and you see that the loading of iridium at similar or same activity and similar or same stability of the catalyst is reduced. Yeah. Of course, that is if you're talking about 25% reduction, for example, that is not moving the needle too much, right? So you have to do more. And in this respect, you apply a carrier because only the surface of the iridium is active. And by doing it with a carrier, you basically make particles which are shielded by iridium or coated with iridium. And then, of course, to save iridium, tremendous amounts of iridium, as shown here on up to 70 to 90%. You can use up to 70, you can use less, 70 to 90% less iridium, compared to iridium black, the standard version. Iridium black is basically solid iridium. Yeah.
Right. Fantastic. So So getting it to an oxide. Now, are the oxides needed for temperature resistance? I mean, most oxide uses are in higher temperature environments, right?
I think they have they're formed automatically through oxidation, and they're more active in the beginning if you have an oxide.
Right, right, and it helps your durability as well, I believe. So, yep,
True.
Fantastic. Okay, so we get the sense of all the thrifting, and I thought this chart that you have here tells the story quite well, just to set the targets for, hey, how low do you need to go, if you will, and on these loadings per gigawatt, how many metric tons per gigawatt, and I think this chart explains it quite well. So, if we're going to be scaling out to 50, and the question is, how much capacity? 50 gigawatts of PEMs, is that all we're going to need, through 2030? Question mark.
And that's gigawatt per year, right? So the question is, how much gigawatt can you produce per year? And of course, the less iridium you need from an availability point of view, the more capacity you can build. Having said that, of course, you also need to have the capacity to build these electrolyzers to basically, on the one hand, coat the catalyst onto the membrane, and then assemble a stack and put that in a full electrolyzer. So that's, of course, another another hurdle to be taken when we're talking about gigawatt capacities more than 50 or more than 50 or around 50 gigawatt. I think this is not there yet, not from an iridium point of view. I think there we have done a lot on the as Heraeus on the thrifting, on the reduction of the iridium loading in these PEM electrolyzers. However, there is still a lot to be done in order to come to such gigawatt scales as presented. Of course, it's ongoing. So,
right. I mean, you're saying it differently. You're working hard to get to this 0.15 type level, scalable to about 5 gigawatts per year as a starting point. But boy, pushing that even further is going to be difficult. Really difficult. So.
Right, but difficult, but not impossible. I think we have R&D in this respect to move that way. I think we are in a good on a good path, and with the latest developments, I'm not sure if you come to that, but when you think about mixed oxide catalysts, we are already at a decent level, I think.
Philip, that's exactly where I'm taking you. So, so let's talk about the scale. How much of this clean hydrogen are we going to need? So here's another chart. This is data that gets published by a group called the Hydrogen Council. They're really, I think, the premier roll-up entity, clean energy entity that's trying to track this. And lots of information on this chart. It shows a collection of proposed blue hydrogen. Today, all the hydrogen that we generate largely is from a steam reformation process using natural gas. And there's some significant carbon emissions. The idea with the blue hydrogen is to use carbon capture as a new technology to capture over 90% of those emissions, making it not perfectly green, but blue, making it clean hydrogen, as opposed to using these electrolyzers to generate green hydrogen. That there's truly no emissions with the fabrication process whatsoever. And just to give people perspective, so there's about 150 million tons of this dirtier gray hydrogen that's produced today. And this entity, the Hydrogen Council, wants to see by 2030 about 45 million tons, 30% of that to be produced either as blue or green. And as unfortunately a little bit too much detail for some folks, but there are multiple electrolyzer techniques that can get you there. We talked about PEM electrolyzers. There are well established a large fleet of alkaline electrolyzers that are already in the field. We'll talk about that more in a minute. And then there's a couple emerging technologies, including the use of solid oxide fuel cell type technologies. I think these are going to be very much focused on chemical operations. It's a very unique technology, but alkaline is the dominant piece, with the question of how many of these PGM using PEMs are we going to need to produce this ramp? And this ramp obviously is only through 2030. Where are you headed? Well, I think the Hydrogen Council, they have eyes for a total of some 600 to 900 million tons of clean hydrogen a year by 2050. They want to see this curve just continue, going off scale. Why do you need all this hydrogen? Well, one is for the transportation for fuel cell vehicles. Some of this is for heavy industry like green steel, green ammonia. There's all sorts of green methane potential applications. Lots of talk about green ammonia and using ammonia as a fuel source for maritime shipping as a fuel feedstock. So a huge number of applications that they want to roll into this. But the reason I show you this data, this is an ominous task, right? How much this cleaner hydrogen are we going to need? It's an awesome amount of material. And so with that, I'm going to let you, Philip, walk through kind of the top three electrolyzers. We have alkaline, of course, is the dominant share. Our PEM, that's the ones we're talking about that are heavy PGM loadings. And then solid oxide fuel cells. Give us a little sense of the maturity of these technologies and cost and where the industry's headed here.
Mm-hmm. Mm-hmm. No, and certainly, I think it's worthwhile pointing out it's never either or, right? So all these technologies have its right to be there. So technology openness, I think, is something which is definitely needed here when talking about hydrogen production in the gigawatt capacities you just mentioned. And alkaline electrolysis is the most mature technology in this respect. I think this is undisputed. It has some disadvantages when it comes to dealing with fluctuating energies, with renewable energies. And that's exactly the advantage of proton exchange membrane electrolysis. It has a rather simple cell design, can deal with high current densities, has a smaller footprint, and this flexibility, this fast response time when dealing with renewable energy. And I think this is one of the major reasons why proton exchange membrane electrolysis is seen as a hot candidate for the energy transition or for the hydrogen economy. And that's why a lot of people are investing in this. And that's why we're also dealing with all the catalytic problems and catalytic challenges in order to make sure that this is going to fly.
Right.
Solid oxide has its right. Absolutely, but to the best of my understanding, and I'm not an electrical or mechanical engineer, but from my understanding, the solid oxide fuel cells, they always work quite well if you have process heat at its abundancy. So you basically can use this process heat to get to the temperatures. Then this is certainly also an option, but it's
I'm glad you brought that up.
That's more niches. Yeah.
That's exactly right. I think the solid oxide fuel cells runs at a very high temperature. And so if you could use that byproduct heat in a productive fashion, that's where the economics of this becomes more attractive. And I think, that's why I think some of the solid oxide applications are going to be geared toward some of these chemical processes that require high heat, where they can take advantage of that heat offtake. PEMs run much cooler and are better suited for a lot of environments. I'm impressed by this cost forecast. You guys see PEMs as becoming the cheapest long term. Is that right?
Yeah, but I would not. I think they're all at the same level long term. So that is, I think, what the message to be drawn from this graph. I wouldn't say this is now the cheapest. It's all in the same range basically, and it depends on the conditions and where you get your material from and so on and so forth. So I think they're all at the same level long term, and they have to be. Otherwise, this will be difficult, I think, to compete.
Understood. So I just wanted to emphasize the solid oxides. I know the composition of these are very much rare earth element centric, right? There's a lot of ceramics that go into this high heat technology to be able to have the durability and the performance they need. Clearly, lots of PGMs, including this iridium that we're talking about, into the PEMs. The alkaline, I know you've got stated here, no PGM catalyst. I guess I have a little bit of heartburn with that commentary because we're going to get into this topic of mixed metal oxides. There are things you could do with the anodes and the electrodes where you can coat these with PGMs that create greater catalytic activity in creating hydrogen and accomplishing some of these electrochemistry reactions that you're looking for. So iridium and ruthenium in the form of mixed metal oxides can coat some of the systems that are used in alkaline. So that I think there can be some PGMs that get involved here. Is really, I think, the point I wanted to stress. And as a segue, I think this is where Heraeus' design trajectory is is taking you. I just wanted to spend just one slide real quick here talking about mixed metal oxides. So often you have titanium anodes, whether they be in a mesh form like this, or they could be a solid anode of whatever dimensions. And these are coated, again, with iridium and ruthenium oxides. Denora, just so their audience knows, is really the kingpin globally of this coating world for these alkaline electrolyzers. They're partly owned, and there's some interrelationships on ownership, but with ThyssenKrupp and with McPhee and basically all the big alkaline electrolyzer producers, where they use Denora coated anodes and electrodes. And I just wanted to state, there's some 220 gigawatts of total installed, largely alkaline electrolyzers in place today. A lot of this shows up in the chlor-alkali industries, chlorine production, and some of the offshoots and different intermediates that they make there. Denora, when you go to their financial report, they talk about their market share. They think there's some 51% of the global market share. But it ends up, these electrochemistry operations that these mixed metal oxides are used in are really far-flung. Everything from copper electrowinning to, printed circuit board electroplating, nickel electrowinning, cobalt electrowinning, zinc, and so forth. All the chlor-alkali industries, wastewater treatment. These systems are used throughout, and it's a pretty significant amount of these minor PGMs that are used. I have an estimate of some 2 metric tons per year of iridium and 10 to 12 metric tons per year of ruthenium go into these various mixed metal oxides. And I know from my client set, lots of people are chasing recyclers. Where can we find end-of-life anodes and help strip and recover these? So I'm helping clients find, some of these recycle opportunities. And basically, you have to chase down the end users on all these different applications to get there. And I do all this presentation on the mixed metal oxides as a setup for Phillip now. Again, back to their design direction, how are they going to get to this design thrifted state? I think you're going down this path with mixed metal oxides. Is that correct, Phil?
Yeah. Yes, but there's a slight difference, which is a morphology, right? Whereas in the alkaline chlor-alkali electrolysis, you basically have this meshes coated with platinum group metals or ruthenium iridium. And here we are actually making a catalyst, means a particle, out of iridium oxide and ruthenium oxide. And that's then applied for PEM electrolysis onto what's called a membrane. And that's usually a fluoropolymer. And we use this on one side. The mixed metal oxides play a role here on the oxygen evolution reaction when splitting water, right? So there's oxygen coming out and hydrogen. For hydrogen, you use platinum or platinum on carbon catalyst. And for the oxygen evolution reaction, you use iridium-based catalysts. And here the ruthenium, iridium, or oxide can be used.
Right. And so again, I set you up here with your slide here on bulk iridium and ruthenium oxides and some of the stability of these different configurations.
Mm-hmm.
Anything you want to highlight?
And I think I think usually, so when talking about water electrolysis, PEM electrolysis, of course you can use a ruthenium. It's actually electrochemical, very active for the oxygen evolution reaction. The issue is you don't have stability.
Right.
And I think what was managed very well by Heraeus Precious Metals is to combine, on the one hand, the stability of iridium with the activity of ruthenium. And this iridium-ruthenium oxide is actually then, on the one hand, bringing stability and activity, and of course reducing the loading of iridium, which helps on the one hand with the cost of the electrolyzer, and secondly also with the availability of iridium. And I think this is really a breakthrough innovation from our labs, which allows really for the scaling of PEM technology to large gigawatt figures. I would have to calculate what the actual figure, but there's room for growth.
I want to state for our listeners as well, this is a technology where the PGMs aren't escaping the system. They're still captive and available at the end of life after the durability of the performance is folded over, that you can recover, recycle, and reuse these PGMs. So none of the metals are lost per se in this technology, but still you want to extend your durability as long as you can to maximize these cycles in between having to refresh your PEM stacks, if you will, with refreshed material. Is that right?
Absolutely. Right.
And so, yeah, I think you guys are onto an interesting path here, where you're showing a great durability with this approach. So, and I think it's just fascinating. This, mixed metal oxides, I think, are an under discussed technology, and I get your point on this is slightly different, but here we are stressing the importance of iridium and ruthenium, two, again, minor PGM metals, fairly small volumes. And so sustainability of both of those elements is really an important discussion. How are we going to recycle this? So is there any other commentary on this you want to, before I go on, Philip?
Yeah, I think recycling is pivotal for the availability and for making this actually also cost efficient. Yeah, the technology, and of course, Heraeus is pretty strong in recycling iridium and ruthenium globally, and we have technologies actually to recycle the precious metals from these end of life stacks. Yeah,
right.
And the question is, of course, if you're looking into stack recycling, what is besides the material value, which is pretty much with the platinum group metals, what about the functional value of some of the components? And I think they're including the fluoropolymer. And I think this is something we need to work out still, or the industry needs to work out still, and we are part of working on that actually.
Right. So I want to kind of conclude the conversation. I want to get into a topic of again, scale and even the motivation. What's behind this hydrogen economy? At the heart of it, it's all about decarbonization, right? We want to reduce emissions both in the fabrication of our fuels and in the consumption of those fuels with these electrolyzers and fuel cells. But I think the thing that just scares the bejeebies out of me ties into variable renewables. And I wanted to spend a couple slides real quick talking about that. Here on this chart, there's a topic about our power grids. Here I'm talking about a subject called our duck curve here in my state where I reside in California. And basically it's a depiction of a curve. It looks a bit like a duck. And it's an expression of how much of the electricity generation requirements fall on the conventional, often fossil fuel-based grids. And it's a chart that shows in California that you're consuming huge gigawatts of demand on an hour-by-hour basis from midnight. And then as the sun comes up and all the solar that we have in California kicks in, suddenly you reduce the load on that conventional power grid. Then in the evening, there's a 3-hour period with quick transition where you get to your peak demand, which is in the evening. And in fact, this is the problem. Our peak demand is in the evening. It's at 9 p.m., 10 p.m. at night around the globe. This is true throughout the planet. And so solar isn't going to help us here. And yet the clean energy transition path that we're on, IRENA and other agencies want to see some 90% of the energy makeup composed of this variable renewable, solar and wind. And the problem with that is multifold. One is, here's a depiction of California. This is a chart from the people that run the power grid in California called CAISO. They have to curtail. They have to turn solar off. People hate hearing this, but in California, we're turning our solar off in pieces pretty much every single day of the year. There's only a few days a year when the systems have fully maxed out that they don't do this. And they track their curtailments, and they've been doing this for years, and I've got it plotted out here. But the curtailments of turning solar off are climbing. And so last year, 2023, this is what our total solar PV production in California was, some 40,000 gigawatt hours of electricity. But they unfortunately had to turn 6.5% of that off, curtailing because they just had too much solar. You can't throttle the gas grid quick enough off and on to be able to respond to demand. Well, electrolyzers and PEMs in particular are very thoughtful in this regard. They are very quick responding. There's a hope that you can construct a system where they can, the electrolyzers can kick in and do more and respond quickly as the power is available. and basically make them daytime running operations. Don't have any excess, run all that excess energy into generating the hydrogen. But then again, a scale discussion, and I'm sorry to be boring everybody on this next chart. This is a depiction of the global power grid and all the electricity generation going on globally. Today, we're at about 30,000 terawatt hours of electricity generation. Most of these clean energy agencies think that we're going to nearly triple by 2050. IRENA has they've articulated a view where they want to set aside a large piece of the future power grid in green here just to generate the power needed to run these electrolyzers, whether they be alkaline, whether they be PEM, doesn't matter. They're all power hungry. Also, you have to set aside a part of your grid going forward for all the charging requirements for the EVs. You basically are going to have to grow today's grid by 50% higher just to support what will be over 1 billion EVs on the road by 2050. So this is really a daunting challenge that we have to grow the power grids. And yet, with all that said, how are we going to store energy? How do you store energy on a daily basis to meet your peak energy demands at night? Or even I could show you charts on a seasonal basis. How do you retain stores of energy in vast quantities to balance your grid seasonally as well as within day? That is the challenge. And this is the sleeper that scares the bejeebies out of me relative to PGMs and the availability of PGMs. How much do we have? I think we're stepping into a space as we push variable renewables where you're going to need more PGMs than we realize just in the energy storage realm. And here I have a chart showing the U.S. Department of Energy. These are the top 12 large-scale energy storage technologies they're trying to develop. Hydrogen and ammonia are by far at the top of the list. Both these are very much PGM-related technologies. Then you get into a whole series of other potential technologies. And when you talk about storing energy, whether it be through batteries or other forms, ends up that hydrogen or some sort of hydrogen and electric hydrogen carrier form, LHC, or an ammonia, which in my mind basically is hydrogen, just in a slightly different form. The levelized cost of storage, hydrogen and ammonia are really the key vehicles, both to storage of vast quantities over long durations, and even to transport it. These are the cheapest means to store energy. So with all that said, as we build out more and more variable renewables, I get very fearful that we're going to put a lot of pressure on PGMs as a block of materials, critical minerals, and I'm not sure we're going to have enough. Frankly, I get really scared in this context. So a three-slide setup there. Philip, why don't you respond to that commentary, if you don't mind?
Now, I think storage will be a topic for sure. I still have, I think, we're talking about a very long time frame in the end, and I still believe in technology. And I give you an example. When I started with the overall PEM electrolysis topic, 2016, again, the loading of iridium was around 1.5 up to 2 grams per kilowatt, or 1.5 to 2 tons per gigawatt. That was 7 years ago, roughly. And now look where we are now. I think we have technology, catalyst technology now at hand, which allows to go down to a loading of 100 kilograms only. But that's a fraction of what was used a few years ago. Of course, there is a limit on what you can achieve, but I think it's not the end yet. And we will work diligently to achieve basically lower platinum group metal concentrations to allow for this hydrogen economy. So with this said, I think your facts are right, but we should not forget that we are in a transition, and new technologies, improved technologies, will be developed as we progress.
Fantastic.
That's my belief, at least. Yeah.
Yeah. No, I think that's the right answer, and honestly, I'm just putting pressure on the precious metals industry as a whole to keep this challenge in front of us. Right, you've got to keep investing in the R&D and the design work to drive this design thrifting to make this as scalable as possible and as cheap as possible. So I think those are absolutely the right points. So Philip, I think I've covered most of the topics I wanted to cover today. How do people get a hold of you if they want to have a conversation on some of these products from Heraeus?
They just contact me via email. That's the easiest. So Phillip.walter@heraeus.com.
Phillip.walter@Heraeus.com. Okay. Fantastic.
Or they contact you and you send it to me. It's also fine.
Or contact myself and I'll help you get in touch with the expert. So fantastic. Phillip, I can't thank you enough. I know this is a technical subject. There's just no avoiding it. You've got to dig into some of the meat. But I thought we did that at a pretty good level today for the average listener. So I really appreciate your time, sir.
Thank you, Matt. And I'm looking forward for the next discussion and the next meeting. I think it's going to be in June, right? So we'll meet each other.
Right. We'll be, I think, co-presenting in the June timeframe. So thank you so much. So, well, with that, let's wrap up. Next week, we're going to continue a little bit of this discussion with hydrogen economy. We're going to get a little bit more deeper into ruthenium and iridium with Mr. Steve Hasselbaker from Furia Metals, a group of a processor a number of folks haven't heard about. Steve is the chief operating officer and founder of Furia Metals America. So we'll continue the discussion with Steve next week. Until then, again, this is Matt Watson. You're listening to Green Rush, Mining the Energy Revolution. We look forward to having you join us again next week. Thank you, everybody. Take care.
Green Rush, Mining the Energy Revolution with Matt Watson.